Today we're going to look at a new type of factoring called sum and difference of cubes. Now that should remind you of difference of squares. Now remember, we could only do a difference of squares. I hope you remember why and maybe take one and try factoring it and recalling that. But there is a pattern for sum and difference of cubes. It's important to know what we're dealing with then. It's an expression with two terms, just like the difference of squares, but both of those terms are perfect cubes. So you need to be comfortable with the perfect cubes. And numerically, we're looking at things like 1, because it's 1 cubed, 2 cubed, it's 8, 3 cubed, 27, 4 cubed, 64, 5 cubed, 125, and you could keep going with that list. So numerically, those are the things we're looking for. In terms of letters, the obvious cube is something like x cubed. But as long as it can be written as something cubed, it is a perfect cube. For example, x squared cubed, which comes out as x to the 6th, is actually a perfect cube. Now, we don't do a lot of those, but just be aware that they're out there. There's more than just x cubed that is a letter that's a perfect cube. So let's take a look at the patterns, and we're going to use the factor theorem to help us figure out what's going on. If you follow this, awesome. If you don't, in the end, there's a formula essentially for doing the factoring, and hopefully that will make sense to you. So we're going to factor a couple of them and see if we can see some patterns. So you can see that we've got perfect cubes going on here, x cubed minus 8 to begin with. And if we use the factor theorem like we did yesterday, remember, you're going to try some stuff, f of something, to get to an answer of 0. And I hope you don't have to strain too hard to put a 2 into that location, which tells us that x minus 2 is a factor. Now, to find the other factors, we're going to do some synthetic division. So the 2 gets divided into, but be careful. We've got 1x cubed, 0x squareds, 0x's minus 8. And that's what we're working with. So we bring the 1 down, we do our stuff. And yes, indeed, it is a factor. So if we take a look at f of x then, it can be broken down as x minus 2 multiplied by 1x squared plus 2x plus 4. Now, if we try to factor that further, it's a simple trinomial, so it shouldn't be too hard, right? All we need are numbers that multiply to positive 4 and add to positive 2. And they don't exist. So this does not factor further. If we were trying to graph this, there's some stuff we could do with that. But if all we're asked to do is factor it, this is where this one stops. So a perfect cube, this perfect cube, has a binomial factor and a trinomial factor, and then it stops. So let's take a look at the next one. Again, we want to substitute something so that the answer is 0. Well, if I'm adding 64, I need to have started at a negative. 64 is a perfect cube. If I put in negative 4, cubed, that's an odd number of negatives that comes out at negative 64 plus 64, and that works. So remember, this is telling us that x plus 4 is a factor. And we can do the synthetic division on that. Negative 4 into, and be careful, because it's 1 x cubed, 0x squared, 0x is in a 64. And, you know, if you're adventurous, you could pause and do this on your own. But I've met you guys, so you're actually still waiting for me to do it for you. So we work our way through. And yes, indeed, we've got a factor. So f of x is equal to x plus 4 multiplied by x squared minus 4x plus 16. And again, simple trinomial in that second factor, you need quotient. So we need numbers that multiply to 16 and add to negative 4. And again, they don't exist. The pattern to sum and difference of cubes, because see, we have one of each going on here, is that they will factor, but the trinomial factor does not factor further. If you end up with a trinomial that does factor out of a sum or difference of cubes, you did it wrong. You made a mistake somewhere. Okay, so there's 2 examples with numbers in. Let's try and generalize it. And you go, whoa, 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 there's no numbers. Okay, you'll be okay. Hang in there. We still follow exactly the same approach, that we want to find something to substitute to get an answer of 0. Now, if I'm replacing the x, I want x cubed minus b cubed to equal 0. What am I substituting? A b. What I'm trying to do here is establish a general pattern, not what happens when it's x squared minus 8 or when it's x cubed minus 8 or x cubed plus 64. I'm saying if I put some perfect cube on the end there, what's going to happen? So this is telling us that x minus b is a factor. And in the synthetic division, it's b that I'm going to put in to the 1x cubed, 0x squares, 0x's, and a b cubed. Let's do it. Multiply and add, multiply and add. I missed the negative. Ah, you guys, come on. Add those together and we get the 0. And again, that's the nice thing about having used the factor theorem along with the synthetic division is we know what's supposed to happen. And so when I wasn't getting the 0 there, I'm like, yeah, I made a mistake. And that's what it was. Okay, so this is telling us that my original function, which I'm going to put in this time as x cubed minus b cubed, factors as x minus b, and then x squared plus bx plus b squared. And see if you can see that. And compare it back to the numerical ones. You can still see above us. I'll slide it just a little. You know, that 1, 2, 4 was 1 x squared, 2 x's, and a plain old number 4. Same thing here. The 1b b squared is 1 x squared, b x's, and a plain old b squared at the end. If you're adventurous, try x cubed plus b cubed on your own. Or just wait for me to do it. Something equal to 0. It's going to have to be a negative b, so that x plus b is a factor. Let's see if I can do the synthetic division right this time. We've got a negative b. 1x cubed, 0x squared, 0x is a positive b cubed. Bring it down, multiply, and add, multiply, and add, multiply, and add. So this is telling us that our original expression of x cubed plus b cubed factors as x plus b, 1x squared minus bx's plus a plain old b squared. Take a look at those two conclusions at the bottom there. Because what I've shown you is a factorization for any difference of cubes on the first one and any sum of cubes on the second one. Let's try and generalize that. Next page starts with what I just had in very messy handwriting and very neat handwriting. And we want to look at that and say, okay, well, how can I do that without going through synthetic division each time? Because I hope you see that clearly there's a pattern. I mean, at least for the first factor, x cubed minus b cubed. That looks pretty similar. It's the cubed root, the same sign, and the cubed root. Same thing on the next one. Cubed root, same sign, cubed root. And that is the pattern for the first bracket. I'm going to pause and write that down. Okay, so that first factor in each case comes from the cubed root, same sign, and cubed root of the original question. But how do you get the second one? And to be honest, what I do is I use the first bracket to build the second one. Once I know that first factor, I use it to build the second one. I'm going to pause, write down what goes on in my head, and then you take a look at it and see if it makes sense. Okay, here's the way I see it. Once I know that first factor, x subtract b, if I square the first term, the x, I get the x squared. Then I change the sign. It was a minus b, now it's a plus. And if I multiply them together, x times b, I'm writing it as b times x. And then I square the last term. It was a negative b squared, comes out as positive b squared. Try and follow that on the second one. X plus b was my first factor. Square the first term, x squared. Change the sign, subtract. Multiply them together. X times b, or b times x. Square the last term, positive b squared. The first factor comes from the question. The second factor comes from building it off the first one. Let's try it with some numbers in because it's actually a bit easier when you see the numbers. The letters tend to kind of freak you out. But first of all, recognize that you have a difference of cubes in this case. It will be two factors, a linear and then a quadratic. The linear is always cubed root, same sign, cubed root. 3 cubed is 27. Now I ignore the question and I use this one to build the second factor. Square the first term, change the sign, and multiply, and square the last term. Notice that what I have is a simple trinomial that does not factor. There are no numbers that multiply to positive 9 and add to positive 3. Try the next one. You're looking at it going 216, are you kidding me? I'm telling you, this is a cubed situation, so play around. We, in our list, had up to 5 cubed is 125. Grab a calculator, try 6 cubed. Hey, that's, what we needed. So this is y cubed plus 6 cubed. So it is cubed root, same sign, cubed root. Now use this to build the next one. Square the first term, change the sign, multiply them together, and square the last term. And there are no numbers that multiply to positive 36 and add to negative 6, so odds are we've done it correctly. We can throw in a couple variations. 8x cubed plus y to the 6th. Part A, x cubed minus 27. I hope you didn't really have to think about what was going on, but if you had to, it was literally x cubed minus 3 cubed. And we kind of wrote that in part B because you weren't that familiar with 216. But notice that those little pieces in brackets are what show up in your first factor. So think about what is being cubed to get each of these. 8 comes from 2. X cubed comes from x. And y to the 6th comes from y squared being cubed. Remember back in grade 9, exponents inside and outside the bracket get multiplied together? Those things are the pieces that make up your first factor. Cubed root, same sign, cubed root. Now use it to build the second one. Square the first term, and I mean square all of it. All of 2x gets squared, so it's 2x times 2x. Change the sign. Multiply the two things together. And square the last term. Y squared squared, y to the 4th. And notice it is a plus y to the 4th. We're squaring. Notice that all of these end with a positive because we're squaring that last term. Part D, same strategy. Think about what is being cubed because that's what's going to create your first factor. 1 is 1 cubed. Same sign. 125, 5 cubed. H to the 9th comes from h cubed being cubed because those exponents multiply to 9. So this factor, this piece, is 5h cubed. Cubed root, same sign, cubed root. Now I'm using that one to build my next one. Square the first term. Change the sign and multiply them together. Square the last term. Square all of it. So it's going to come out positive 25 h to the 6th. And if you were particularly bored, you could actually expand that. Every term in the first bracket multiplied by every term in the second bracket. Go through and collect like terms, and you'd find out it really does simplify to 1 minus 125 h to the 9th. So just a new factoring strategy. Have a chance to practice that on page 182. Remember the patterns and see how that goes.